Look at this stamp. Issued by the Royal Mail in 2015, it honors Colossus as the world's first electronic digital computer. It is a compelling claim for a machine that helped win the Second World War. But by modern definitions, that title is inaccurate. Colossus had no internal RAM, it was incapable of numerical operations, and it was not Turing-complete. It could not run a flexible, swappable program. If Colossus was not a true computer, we are left with a paradox. How did a machine with such limitations crack the most heavily guarded cryptographic system of the German High Command right on the eve of the Allied invasion? By late 1943, the intelligence war in Europe was operating on a razor's edge. The Allies desperately needed a way to intercept and decipher German strategic communications fast enough to act on them before the invasion of Europe. The reality of Colossus is found in how it functions as a physical solution to a specific mathematical bottleneck. When we think of German codes, we think of Enigma, but Enigma was largely used by field units. For their highest-level strategic communications, the German High Command relied on a system that was far more complex. This is the Lorenz SC40, which British codebreakers referred to as Tunny. It was an advanced cipher attachment that operated on a completely different scale. Instead of operators manually keying in Morse code, the Lorenz system was attached directly to a teletypewriter. Messages were typed in plain text, converted to binary code, encrypted automatically, and transmitted at high speed. The encryption relied on 12 interconnected wheels. Two sets of these, known as the chi and psi wheels, added obscuring characters to the original message. Crucially, two motor wheels dictated whether the psi wheels moved or stayed still, creating a staggered, stuttering output. The result was a cipher stream that looked like perfectly distributed random noise. Because it lacked the predictable, human repetitions of manual encryption, traditional code-breaking methods failed. The solution came from a 24-year-old Cambridge student named Bill Tutte, whose expertise lay in the highly abstract realm of mathematics. Before the war, Tutte and his colleagues published a foundational paper exploring the relationship between graph theory and electrical circuits. He was accustomed to breaking down complex, interwoven systems into their base logic. By analyzing statistical patterns buried in intercepted binary traffic, Tutte deduced the exact mechanical architecture of the Lorenz machine without ever seeing the hardware. He realized that the Lorenz encryption was not just a mechanical scramble, it could be represented as a strict equation of linear algebra. The equation states that ciphertext, C, is the result of adding plaintext, P, to characters produced by the chi and psi wheels. If you isolate the chi wheel sequence, you strip away the first layer of encryption. Tutte bypassed the physical machine entirely. He stripped away the metal and the rotors, reducing a mechanical espionage tool into a solvable math problem. To solve that math problem, Tutte devised what became known as the 1+2 break-in. This method specifically targeted the vulnerabilities of the first and second key wheels. This diagram visualizes Boolean delta differencing. By comparing adjacent bits of intercepted code using an exclusive OR operation, analysts could strip away the randomness. Executing this formula repeatedly across the entire message length, you count the number of times it yields a false or zero result. If the wheels were in the wrong position, zeros occur 50% of the time, but when correct, the tally exceeds a threshold, creating a statistical bulge. The logic was flawless, but the execution was the problem. A single message could be thousands of characters long. Calculating the delta differencing by hand across all possible wheel start positions would take years. Tutte had defined the logical steps required to break the Lorenz cipher, but those steps were purely theoretical if manual calculations couldn't keep pace with a live war. The solution came from Tommy Flowers, an engineer at the General Post Office. He proposed using thermionic valves, vacuum tubes, to perform high-speed electronic counting. This is the result, the Colossus Mark II. A massive installation built from 2,400 vacuum tubes, designed entirely to run Tutte's algorithm continuously. To feed data into the machine, Renz prepared the intercepted German binary traffic. They punched the characters into the paper tape and glued the ends together to form a continuous loop. That loop was loaded onto this mechanism called the bedstead. Optical photocells read the paper tape at a speed of up to 20,000 characters per second. Colossus didn't have software. To set up the new algorithm, operators physically rerouted cables and flipped switches on control panels. Colossus functioned as a direct physical manifestation of Tutte's linear algebra equation, hardwired to execute a specific algorithm at massive scale. Once the tape was spinning, Colossus executed the Boolean XOR logic, comparing impulses and tallying the false results. When the counter found the statistical bulge, it printed out the correct starting positions of the keywheels. The speed was critical. Mathematical calculations that would have taken human analysts weeks were now completed in just hours. By June 1944, this accelerated processing provided the Allies with a vast amount of high-level intelligence from the German High Command, securing information about troop deployments right before the D-Day landings. The successful invasion of Fortress Europe was heavily guided by this specific synergy, the abstract graph theory of Bill Tutte, mapped onto the hardware engineering of Tommy Flowers. So we return to the initial question: was Colossus a computer? Historians look at this through an analysts category, applying strict modern definitions to historical objects. By those metrics, it falls short. Tommy Flowers himself characterized Colossus not as a computer, but as an electronic processor, and that distinction matters. Reducing history to a race for who built the first computer obscures how theoretical cryptography was forced by the pressures of war to evolve into digital communications engineering. Colossus remains a significant milestone because it proved that high-speed electronic components could solve complex logical problems in a real-world environment. How much do you think semantics matter when we record the history of technology? Let us know in the comments below and subscribe for more deep dives into the engineering that shaped our world.